Okay, we have seen a simple naive mechanical model of DNA supercoiling that mimics what we see in experiments. I recall a bit. The experiment is like this. We have magnetic tweezers. There is a bead attached to DNA, which is also attached to a solid surface. When the magnets are turned, the bead is also turning, and this exert a certain torque to the DNA molecule. Okay, so the DNA supercoils. All right. And these are typical tracks that we see in experiments that we have already seen here. This is the number of turns that can be positive going with the same turns, natural turns that the double helix has. Okay, so this is an over twisting of the helix. This is an under twisting of the helix on negative turns. And here is the stretching force. Okay, so when the force is of 0.2 piconewton, we have this black curve. When the force is 1 piconewton, we have this green curve. And when the force is 5 piconewton, we have these brown curves. Okay, and all right, so here we see at 0 turn. Okay, so the DNA is just stretched like this. Okay, and the higher is the force, the higher is the DNA extension. The extension is the distance between these 2 points. Okay. When the force is about 1 piconewton or above, then one see an asymmetry. For forces below that, you know, these curves, what is called these rotation curves, are asymmetric. Okay, so either when I apply plus or minus turns, I have the same shape. All right, we're not going to discuss the asymmetry. There are models that can deal with that. We are going to introduce a simple model that is applicable to these situations of small forces. Okay, and the model that we are going to discuss today is the two-phase model. So what is the idea of this two-phase model? So if we imagine a situations where the DNA is supercoiled, I can divide my supercoiled molecule into a region, plectonymic region, where I really have this entanglement of, really this, actually the supercoiling is here, and another region where the DNA remains more or less stretched. Okay, so in these experiments, the excess linking number, or the number of turns that I apply to my beads, is fixed, or also the supercoil density, what I call delta LK divided by LK naught, where LK naught is the natural linking number density of relaxed DNA. Okay, so what does it mean, the two-phase model? The two-phase model assumes that there are two phases, and therefore each phase has its own free energy. This is our free energies per unit of length. Okay, this S is the free energy of the straight phase for a given supercoil density sigma. Okay, and P is the free energy of the plectonymic phase for a given supercoil density sigma. And we are taking these two forms of these free energies, and these are shown here. Okay, so for the first free energy, we write minus A B divided by 2 sigma squared. First of all, well, we discuss only the symmetric case, the low force case, so I think it's reasonable to expect that this free energy is well described by a sigma squared type of behavior in sigma. Okay, and here dashed dotted line is the free energy S of the straight phase. We know that, okay, if we have no turns, okay, sigma equal to 0, delta LK equal to 0, then the molecule is just stretched. Okay, so the free energy of here at sigma equal to 0 must be of the stretched phase here, must be lower than the free energy of the supercoiled, of the plectonymic phase. Okay, right, but at certain point there has to be some crossing of these two free energies, because we see plectonyms appear. Okay, therefore, for sufficiently large sigma, there should be supercoiling at some point. Okay, so we expect, if we want the crossing, this coefficient C must be larger than the V. But the minus A takes care of the fact that this, the stretched phase free energy starts from a lower point here. Okay, so we have to deal with these two free energy, and this we know how to do this from thermodynamics. This is what is, if I minimize global free energy, I obtain a Maxwell construction, which is the double tangent constructions connecting 2 points here. Okay, so what is the meaning of this double tangent construction? If my linking number, so if the number of turns here is small, and small means remains within this region, okay, below sigma, below the value of sigma s, then I am just in a stretch phase, and the free energy is just the s of sigma. In this region, from and sigma is between sigma s and sigma p, actually I have a phase coexistence. This is very similar what we have seen in thermodynamics, for instance in the van der Waals model, the coexistence of a liquid gas. Okay, actually for any value of sigma here, for instance 0.05, 5% of supercoiling density is actually my state phase separate in a state where the stretched phase has supercoiling density sigma s, and the plectonymic phase has a supercoiling density sigma p. Okay, and we are going to do this analysis and doing this construction a bit later, but in the next 2-3 slides we are going to discuss a bit more into detail the free energy of the straight phase. Okay, for the free energy of the plectonymic phase, for the free energy of the straight phase, sorry, we can do some analytical calculations of these phases is quite simple. Is a piece of twistable worm-like chain, say, that is under tension, and to which there is a certain linking number associated and fixed linking number. For this phase we are just taking the assumption that this is given by this, and this C can be seen as a kind of fitting parameter that we adjust at the end. Okay, now let's discuss about the free energy of the straight phase. Okay, so what is a straight phase? What I'm describing here is, for the straight phase, I'm taking the total energy as the contribution from the worm-like chain energy that we have seen, that contains all the bending terms, the stretching force, okay, z, small z is end-to-end distance, okay, F is the force, and we have the twist energy. So C is the twist modulus that we have seen in previous lectures. Okay, and omega 3 squared is the twist density. Okay, and we have to impose that there is a constant linking number here, and this is the difficult part. Okay, so it's not a free fluctuating molecule, but the two ends of the molecule, there is a certain rotation angle imposed to the bead in a magnetic tweezering experiment. So there is a constant and fixed delta Lk. All right. So let's consider one simpler limiting case, right? That we consider a straight limit, where the end-to-end distance is equal to the contour length of the molecule. So the molecule is not fluctuating. So imagine a straight molecule, but it's still, there is this linking number constraint. Because the molecule is straight, there is no bending energy. So the worm-like chain energy is just 0. there is just this term to evaluate at constant delta LK. So how do we do this? So, okay, this one is 0, so it's not there. Then instead of here Fz, I have F times L, fixed L. Then I have this one. For this term, I'm using what is called the Parsifal Identity, and the integral from 0 to L of F squared can be written in Fourier Components, sum over the Fourier modes, Fourier modes F tilde of Q, which are the Fourier transform, which is the Fourier transform of f of s. Okay, so I go in Fourier space. All right, so this Q contains Q equal to 0 term and the Q different from 0. Okay, so I separate the two. Okay, this one is the Q equal to 0 terms, and these are all the Q different from 0 terms. Okay, and tilde denotes the Fourier transform. Okay, I go to Fourier Components. Okay, and what is actually omega tilde Q equal to 0 component of this twist density? Okay, this 0 component is nothing but 2 times the total twist, because you know, if I would have to calculate the omega 3 for a given Q, then I would have an exponential IQS here, but because Q, I'm interested in the component Q equal to 0, this is just the total twist times multiplied by 2 pi. But because we are considering the straight limit here of our molecule, the twist is also the excess linking number. There is no right, okay, in other words. So the twist is also equal to the linking number. So because I want to fix and have a fixed linking number, okay, in this, it means that I fix the Q equals 0 component of the Fourier transform of omega 3. Okay. Therefore, it's very easy. This term is fixed because it's just delta LK. It does not fluctuate. So when I evaluate my partition function, I have to integrate over all configurations in the twist here, and this partition function will pick up these terms. These are the terms that I have to integrate, and this will be some additional contribution. Actually, I want to calculate now. Well, sorry, still I'm not doing the integration. I just report these calculations from here to here. I substitute this one, and I will have non-zero momenta contribution. Okay, so now when I calculate the next step to do the partition function will be integration on these non-zero momenta contributions, but this will give a normalization factor that is not relevant for us for the free energy, because finally what we are interested in the free energy is in terms which are dependent on the force, okay, that comes from here, and terms which are dependent on the linking number or on sigma. Yeah, remember the linking number is also equal to, is proportional to the sigma density. So this term actually comes down to the free energy as a constant and gives rise to this sigma squared because of delta LK squared. Okay, where I used quantity that I defined in previous slides. Okay, is h squared. Okay, so this is a very simple and straightforward calculations. I recognize that the non-zero momenta they give a normalization term, an additional constant to the free energy, which I'm not interested in, and it's just the trick of using a constant delta LK brings me this factor. Okay, so, and this is for the straight limit. Now we want to go, of course, to the next more interesting case. So we start from the same energy, but we are interested in a fluctuating molecule, right? It's not straight anymore, so the end distance is a z, is a fluctuating variable now. It's not capital L anymore. Okay, but we are considering situations where the stretching is quite strong, and in this strong stretching, the tangent to the curve is almost aligned to the directions where the force is applied, the z direction. So if I look at the tangent in different points of my curve, this tangent is almost parallel to z, and it has a very tiny component u, which is perpendicular. So if the tangent t is oriented mainly along z, this u is oriented along x and y. So u is a two-dimensional vector, okay, but this treatment is very similar to what we did in for the worm-like chain. So now case B, we are interested in fluctuations, okay, and therefore in this situation. So I have now z, a fluctuating quantity. I have my energy that is also fluctuating, and it's larger than 0 in general, okay. So there are two terms in here that I have to evaluate. The term number 1 is the same that we know from the worm-like chain model, all right. And this is well, there is this contribution. Z is L minus the fluctuating part, okay, and this fluctuating part together with the bending contribution, this fluctuating part gives rise to this term. Okay, so what are the u, q? Are the Fourier component of this two-dimensional vector. So u is a function of s, which is the coordinate along the curve. When I Fourier transform, it becomes a u of q. Okay, and okay, so this is something that we have seen on a lecture on the worm-like chain. Okay, and this is an expansion in small q. So to lowest order, I have a quadratic term in u, and then I have higher order terms, u to the 4th, that I neglect. Okay, so in this strong stretching expansion, I just keep the lowest order terms in u. Okay, and here I deal with a Gaussian model, right? This finally is exponentiated, and I have to calculate the partition function. We have discussed these are like harmonic oscillators, and this is a kind of, I can interpret as the stiffness of every mode. Every mode has its own stiffness. Okay, right. And there is the term 2. For the term 2, I'm applying exactly the same trick that I did on the previous slide. Namely, I write this using the Parsifal identity as Fourier component. Okay, then there is the omega 3, the zero momentum component. Okay, that fixes the constraint. Okay, for the zero momentum component, I do exactly the same that I did in the previous slide. Okay, you remember here I had delta twist squared. Okay, and now I transform it into delta LK minus right. Now the difference compared to the previous slide is that I don't have just delta LK, but I also have a right contribution. Plus, all what is here are terms which are higher, are momenta, finite momenta. Okay, Fourier components of this omega 3 in higher Q. Okay, I'm not interested in this. They will just be integrated out. Okay, so when you do that, okay, now this is the difference. Okay, so I have the right and I have to evaluate the right. The right is a fluctuating quantity. Okay, it depends on the conformation. So I have now to do calculate the partition function of this total energy, and I have to take into account the fluctuations in U and the fluctuations in the right. Okay, so the right, it's a small quantity. I can and that will be an exercise for the students to write this right, okay, in terms of this U vector. Okay, if you do that, you realize that the right is order U squared. Okay, so because we are interested in the lowest order, and this is a strong stretching expansion, when I square this quantity between parentheses, I get delta Lk squared, and then minus 2 Lk right. But because the term right square is higher order, I neglect it. Okay, so what I have here, it's a fuller right. Okay, so I have to take the fuller right, and I can actually, using this strong stretching expansion, it's a simple exercise to express this fuller right in terms of the variable u. Okay, the small parameter, the small variable u. Okay, and I combine the 1 and 2, I get this expression. Okay, so let's see. I get beta E total divided by L. Okay, so the first term is coming from here. It's minus beta F. I divide by L here. Okay, the second term is coming from this one. It's exactly the same that I had before, okay, in the previous slide for the straight molecule, and this one is here. Okay, so if I go back to the previous slide, I recognize just these two terms are coming from the straight molecule conformation, but now I have this extra term. Okay, let's see step by step. The diagonal part of this extra summation in Q comes from this. Okay, from this one. It's just a simple rewriting here. And the right that was here, that was multiplying the linking number, okay, multiplying C and this factor. Okay, now what I have to do is I have to do this exercise, and I express this right in Fourier components UQ. And if you do that and you collect these values, you see that this right gives rise to the off-diagonal terms of this matrix. So remember that this U is a two-component vector. It's a vector pointing in lying in the xy plane. Okay, so its Fourier transform is also a two-component vector. Okay, with the x and y component. Okay, so that's why this matrix is a 2 by 2 matrix. Okay, the diagonal part is from pure bending fluctuations, and the non-diagonal part are coming from this right fluctuation. Okay, but this still it's a Gaussian model. So now to calculate now the partition function, I have to integrate over all possible values of these amplitudes u of q prime, and so this is a sum over q, so all the modes are independent for different q's. Okay, and the calculation is, well, requires a few steps of calculations. I skip it and I give just the final result. Okay, I give the final results that I obtain by integrating these the partition function, the Boltzmann factor that contains this term. Okay, this comes out from my these are constant terms. So when I look at the free energy, I have to multiply by this by kBt. So there is a first term minus f that comes from here. There is this constant term that is this one multiplying by this times sigma squared. Again, I have to multiply by kBt, which is here. Okay, and this evaluation of this quantity gives rise to these terms. Okay, this one here that couples to the terms with the force. This is something we had already for the worm-like chain, and this additional term here. Okay, so this is the end of these calculations. It means that we have a good expression for the free energy of the stretched phase. So this calculation was done by Morris and Nelson and others around the same time. Okay, and it shows that these thermal fluctuations enter and couple to the twist variable. So you see that although if you go back to the Hamiltonian here, to the energy, you have A, which is as we know, it's A is the bending persistence length of the worm-like chain. C is the torsional stiffness or torsional persistence length of DNA, and in the energy they are separated. But this constraint of fixing the linking number somehow couples them, and there are terms where C and A, they enter together. Okay, and so it means that the bending fluctuations that are here coupled and give rise to so what in the previous model there was just this factor 1 when you have the stretched the straight molecule limit, now is actually coming with the more complicated terms. So this is called the effective torsional stiffness. So the calculation is presented here in this work. Also, I follow a bit the strategy of this paper. Right, it's different from the original work. This paper uses this strong stretching expansion. All right, so now that we have the free energy of the stretched phase. All right, and we can, for instance, calculate the extension of the stretched phase. For when we know that when we have the free energy, if we go back to the form of the energy, right, by taking derivatives with respect of f enters only here. I pull down from my Boltzmann factor the z. So the free energy derivative of the free energy with respect of the force give rise, as we know well, give rise to the average. So I can calculate the average extension from that, right? So if I have now the free energy, I take the derivative with respect of the force and I get the extension. Okay, so this is a simple calculation. I see it straight what comes out of here. When I differentiate with respect of f, I get 1. When I differentiate with respect of f, here I have this f times this 1 over square root. It's a square root factor. It brings down this factor 1/2 that I can bring out inside this this factor, and I have kBt. So if I stop here and I take sigma equal to 0 and I forget about the rest, this is the force extension relation that we have seen already for the worm-like chain model. Okay, the one when F force goes to infinity, average Z is equal to L. This is a straight limit. Okay, very high forces limit. But on top of that, we have a term which depends on sigma squared. Okay, and this term on sigma square, okay, tells us that the molecule actually gets contracted. I have a minus, increasing the number of turns. So I have the following situations. If I don't apply any turns here, okay, and I have my molecule in my magnetic tweezer experiments, and just by applying a small number of turns, sigma, small supercoiling density, I get a small contraction of the molecule. And this theory tells us that this contraction, Z over L, is quadratic in sigma. Okay, and this is also seen in experiments, and we discuss this and we show this in the next slide. Okay, so we are now discussing the stretched phase. Okay, and now we are looking at the final things. So we have so far discussed very much the detail of this free energy, and we have shown the extension in the stretched phase. Now we are interested in this coexistence region. Okay, so what happens in this coexistence region is that the free energy is composed by two terms. Okay, the free energy density of the straight phase with its value of sigma s, and the free energy density of the plectonamic phase with the value of sigma p. Okay, these are two different values, and these are fixed. They do not depend. So they are fixed, right? Okay, so if I am here at the supercoil density of 0.05, I will have a certain percentage of my system, a fraction, xs will be in this state, in the supercoil, in the straight phase, and a fraction of it will be in the plectonymic phase, xp. Okay, so the sum of these two fractions must be equal to 1. Okay, and also the linear combination of fraction of S phase times the supercoiling density of S plus the fraction of P supercoiling density X of P supercoiling density of P is equal to sigma. Okay, so this is the Maxwell construction of these two. Now, to calculate the extension, again, I can do exactly the same. So I take the free energy, the total free energy now that it's the appropriate one in this region, okay, and I differentiate with respect of f with a minus sign. Okay. Here, however, I make the assumption, and also it makes sense that this assumption that this plectonymic part does not contain the force, is force independent. Okay, so actually this derivative acts only on S and not on P. Okay, so actually it comes out a very, very intuitive formula. And if we go back a couple of slides, allow me to go back of a couple of slides. First, have a look at this formula. Okay, this formula is telling us that the extension is the fraction of stretched phase times the extension of the stretched phase, which makes a lot of sense, right? Because the plectonymic phase does not contribute. Let's go back. The plectonymic phase does not contribute to the extension, so I wanted to show this figure. Okay, so we are here. Only the stretch phase contribute to the extension, Z. The plectonymic phase does not couple to the force, does not contribute to the extension, right? Okay, and that's why. So let's go back to the slide. Okay, right. And now this x of s, I can also write it in terms of sigma, because I can solve these two equations for x of s and x of p. The x of s is just this combination. Okay, it's linear in sigma. Okay, so finally we can collect the results, and if one uses this theory, one needs to do a bit the detail of the calculations. That now I describe these calculations, just not showing all the steps. Okay, but the end result is that this model predicts a certain shape of DNA extension versus linking number that is shown here for different values of the forces. Okay, so let's see it back here. So for small linking number, the model predicts a parabolic piece of parabolic shape that is discussed in the previous slides, the slide before this. Okay, that's the straight phase from here to here, from here to here. Okay, the extension is it has a constant. It has at sigma equal to 0 at certain value, and this is and then depends on sigma squared with a negative curvature. At this point is one enters in the coexistence region. Okay, and in the coexistence region, the extension is just linear in sigma. You see here the f does not contain sigma. This is evaluated at sigma s. Okay, so the only dependence on sigma is here, and it's a linear function. Okay, and it's going down like like a straight line. Okay, going back to the previous calculation, right, of this curvature, one sees that as okay, no, I think there is a mistake here. It should be to the power 3/2. Okay. Oh, right. So I wanted to show this, and I realized that there is a mistake here, because when I differentiate this with respect to the force, I get a power 3/2 here, not 1/2. Okay. Okay, so you should correct this one. But you see, when the force is increasing, getting larger and larger, the total coefficient of this term sigma square becomes smaller and smaller. So this is a parabola which has lower and lower curvature. Okay, and this is what we see back here. So when I increase the force, these are for 4 different forces. When I increase the force, then the curvature becomes smaller and smaller, and this line has a smaller slope. This was similar to what we see in this naive mechanical model, but this actually turns out that these data are quite close to the experimental, so to the actual magnetic tweezers experiment.